Okay, in this case, we are going to continue with our transformers, but this time that is focusing on the rating of what transformers. So basically, you're going to see that all transformers, they are being rated in kVA. All transformers are rated in what? Rated in kVA, kilovolt amperes. So you work with what? Volt amperes. So that is the basic part that you're gonna be given. If they give you, say, the rating of a transformer, you know that is what our S, our apparent power, which is kVA. All right, but as part of your calculations, I'm not gonna dwell into much of the theory part. I want us to understand calculations which can be made just to add from what we had before. We can consider the transformer ratio, all right, where we can obtain the tens ratio that is referred as the what? The transformer ratio. The transformer ratio or what? Or the tens ratio. They can ask in that manner. All right, so the transformer ratio is taken from the voltages, all right? V1 over V2 is supposed to give us N1 over what? N2. That is our tens ratio. When we are given current, that's I2 over what? Over I1 from the currents, all right? Where V1 is the primary, V2 the secondary, all right? Remember, we dealt with this one for the primary side and two for the what? For the secondary side, depending with the textbook that you're using. Some they use P, the subscript P, subscript what? S for the secondary. So I'm just going to use 1 and 2. So that is it. N being what? The number of tens. V, that is the voltage that you are given, the normal voltages, all right? Primary and secondary. And also, you need to understand the EMF equation calculations of the EMF equation. It's another aspect that you're required to know in your syllabus of what? Of a transformer. All right, it's another aspect, very, very important uh, for you to understand, which is given the EMF equation. It is basically a condition where we are saying it is the magnetic flux that links both the primary winding and secondary winding due to the which is actually an alternating flux, all right, which is considered in the calculation of what the EMF equation. So you'll be having the maximum flux in your calculation, which is equal to 4,44 times the frequency times the maximum flux. This is the maximum flux times the number of tens, which can be on the primary or on the what? On the secondary. All right. Remember the flux, guys. We dealt with this one before from our E-Tech, from our electrotechnology N3. All right. So if this is E1, this is going to be N1. All right. If this is E2, this is going to be N2. This is the consideration of the formula. So that's it. The frequency F is our frequency. All right. Our frequency in what? In hertz. And the maximum flux. There we have got the maximum what? Magnetic flux. This is our maximum magnetic flux, which is measured in what? In Weber's, WB, Weber's. And E can be E1 or E2. Those can be induced EMF, simply induced EMF can be E1, can be E2, and any number of tens. Number of what? Of tens. So for the number of tens, when I asked you to calculate or to determine number of tens, round up values when calculating, you round up values when given what? When given decimals. When given a decimal, you round up the value from our mathematics concept, all right? Whenever you're given a decimal, maybe it's on your calculations, just round off, you round them up. So that is it. And the relationship between here, we can also have the relationship between the flux and the magnetic flux density. So it follows that the magnetic flux is magnetic flux density times area. So magnetic flux density can be calculated as flux over what? Over area, which is measured in what? In Tesla. Magnetic what? Flux density. That will be magnetic flux density. In what? In Tesla. So this is it. So that's a relationship which can be obtained. So if this is maximum flux, remember these two, they are proportional to each other. Magnetic flux and magnetic flux density are directly proportional. So if this is maximum, this is also maximum. All right. That is the condition that can be used. All right. So this is part of your EMF equation. Just understand the basic. It's very, very important just for the basics. Then the last part that I want us to consider is given as the staking factor. All right. The staking factor. All right, which is also referred to as the lamination factor. All right, the lamination factor. So that's K. Some they use KS. All right, for that staking factor. It is the ratio of the effective cross-sectional area of the transformer's core to the physical cross-sectional area of the transformer's core. The ratio of the effective cross-sectional area, effective of the transformer, to the physical cross-sectional area. All right. So that is given as what is Ks, where Ks, the staking factor, is equal to the maximum flux or maximum flux density over B times A, the area. Magnetic flux density times what? Times area. So it's a constant, it's a factor. This one is a constant. So meaning to say, the maximum flux here can be made the subject. This one can be the subject. A can be the subject. Those are the conditions that you are going to have. That is it. This is what you're going to need as the basics. As the basics, this is what you are going to need. So I'm just going to put an example to utilize these formulas. Let us consider this question that we are given here as an application just to understand what we just had. Here we are given a 20 kVA. 20 kVA. What are we given? The kVA is what? The rating of the transformer. Apparent power, or just write kVA. The rating of the transformer, 20 kVA, and frequency is given. And also take note, guys, the kVA is simply voltage times what? Voltage times current. So it can be V1 times I1, it can be V2 times what? I2. Voltage times what? Current. Do not worry much about that. So we are given the frequency 50 hertz. This is 1100 over this V1 to what? V2. So you're given the value of V1, 1100 volts, V2, which will be 240 volts, single phase transformer. All right, here's a gross cross-sectional area of, so we are given the cross-sectional area, which is the gross cross-sectional area of 0.008. This affects our staking factor. When you are given a gross, when you are given the gross area, cross-sectional area in our staking factor here, when you are given the gross cross-sectional area, it follows that our Ks is a value that is less than 1. All right? It will be a value that is less than 1 in your calculations. All right? And sometimes you'll be given in terms of the values, they can give you the net area. All right, you can be given a condition where you have got the net area. In that case, it will be equal to 1. Our Ks will be directly equal to 1. All right, so that means here we're gonna simply use what we are used to in our calculations. But in this case, that's why you're seeing that the staking factor is 0.93. It's less than because of the area that you're given here. So determine the number of primary and secondary turns. All right. So we are supposed to determine the primary and what the secondary turns. If the maximum flux density is, so we are given the maximum flux density, all right, which is 1.5 Webers per square meter. It simply means a Tesla, that one, all right? That's a Tesla or Web per watt square meter. And the staking factor is given as 0.93. All right. So we need to calculate N1 and N2. What can we do? What can we actually do? All right. Let us figure out where we have N1 and N2 from our EMF equation. We have got N1 and N2 from the EMF equation. Remember this condition, E1 and E2, just taken from V1 and V2, all right? So from the EMF equation, we can consider that, but we do not have the maximum flux. All right, let us take that formula first and see. It's simply from what? EMF equation. From EMF equation. So that's E is equal to 4,44 times flux times frequency, sorry, times maximum flux times N. So if it is, let's say we're to find N1, it means this is E1, N1. And E1 is equal to what? Simply our V1. So if we are to make N1 the subject, it was going to be equal to E1 over what? We're going to divide by this 4,44 times frequency times maximum flux, magnetic flux, which we do not have this one. We have got E1, we've got F frequency. So where can we have the maximum flux? You have to ask yourself now, from the information that you're given, how can we obtain the maximum flux? All right, is there any information? All right, let's check. Since we have got the staking factor, there is a maximum flux here. We can make the subject maximum flux is going to be simply equal to the product of this. All right, so that's BA times what times KS. All right, let's see. It's mathematics, guys. Play around, change of subject, like that. So that's B times A times what? KS. Do we have the maximum? Yes, we have got this, and we've got this, we've got this. So that is, we have got this, guys. The area, remember, we are given here. So let us substitute and find our maximum flux, magnetic flux. Magnetic flux density is given as 1.5. So that's 1.5 times area, 0.008 times our Ks, 0.93. So that is it. We have the maximum magnetic flux of, that was going to be 0.01116 Webers, which we can just write to milliwebers, 1, 2, 3. So that's going to be 11.16 milliwebers, or simply multiply by what? 10 to the exponent of 3, opposite of that. So, or you can just take this value as it is. So now we've got this value. We can calculate the number of turns, which is N1 for the what? For the primary. All right. So E1, same as what? As V1. We can substitute our V1, 1100 over what? 4,44 times the frequency, 50 hertz. The maximum flux We just calculated it. 0 point this, or this, whatever that you understand, guys. All right. So that was going to give us N1. And for this number of tens, it was going to be 443,992. And like I say, dealing with the number of tens, you must round up your values, all right? When you're dealing with what? Number of tens. When given a decimal, round up your values to the next whole number. So to the next whole number, this will change to 4. So that's 400 and what? Sorry for that. 444. We're simply gonna round up. So that's what you're gonna have. These are the number of tens. So it approximates to 444 tens. All right. So that was the idea. Since we have our maximum flux, we can also do the same to find our N2. All right. Oh, so for N2, we can even use the transformer ratio since we've got V1 and V2 and we've got N. So we can use this transformer ratio, which is fine, or we can just continue with the formula in order for us to find N2. It means this will be N2, this will be E2, this will be 2 like this. So that is what you're going to simply need, meaning to say we're going to use E2, where E2 is equal to what? To V2. So that's it. Remember, we already calculated the maximum magnetic flux here, so just substitute. So that was it to find our N2 for the secondary side. E2, that is our V2, which is 240 volts. All right, over what? 4,44 times the frequency, that is 50 hertz, all right, times the maximum flux, which is 0,01116. So that is it. We're going to find our N2 from that, the number of tens on the secondary side. On the secondary, which is 96,87 tens, and we have to round up to the next what? Whole number. So the next whole number is what? 97. So that's 97 what? 97 tens. We have our N2 from the given information that we have. So that was it. Like I said, we could have played with our transformer what? Ratio. V1 over V2 is equal to N1 over N2. So you can use the N1, remember? We calculated N1, so it was going to be like this. It was going to be like this. This is another way. We have N1. This one, we have it. We need to calculate N2. So V1 over V2 is what we are given from our information here. V1 over V2, 1,100 over what? 240. So we can simply have it 1,000. 100 over what? 240 is equal to N1. We have N1. Remember, we calculated N1. It gave us 444 tens, the one that we calculated first. We had that one. We do not have N2. So we can calculate our N2. Here we're going to take this to the other side. So that's N2 is equal to 444 times, you remove this one. So to get rid of this, you multiply by the reciprocal, 240 over what? 1,100. So that was going to give us N2, but just round it off because we are using a rounded off values. So it's going to just change a little bit, but let's see what you're going to have here. That's over 1,100. So this is it, 96,873. 96,873, which simply to the next, it's going to approximate to 97 what? 97 tens. Same as this one. So you can even go back to the transformer ratio. Apply that, you're going to have same answer for that. So that is how you'll be given these questions, guys. Just use the formulas, all right? Directly use the formulas, understand your formulas, and learn to mix up the formulas from one formula to another. If you see that you have a formula but something is missing, another quantity is missing, find another formula which has that quantity that is missing on your formula, calculate it, and then substitute into the formula where it is what? Where it is needed. That is how you play around with these questions, all right? So do more questions as an individual. Just try to do as many questions as you can.